Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a concept of the jet propulsion of a tank with an orifice. So in our last lecture, we have discussed the theory part of this jet propulsion, and we have discussed about the definition and the objective and applications, types, advantages, disadvantages of jet propulsion. So in this, I have taken the jet propulsion application on a tank where an orifice is fitted that. So this orifice actually fitted like it will be act as a nozzle. So why the nozzle is used? We know that to increase the velocity. To increase the velocity, nozzle is to use. So on behalf of nozzle, here orifice is fitted at the exit of this tank, we can say. So for this concept, I have taken a diagram, and this diagram was taken from the book. Here we can see a tank which consists of some volume of water with a height of h, okay, with a height of h, and this tank is installed with some wheels, okay. This tank is, you can say, it is situated on the two wheels, and these two wheels are need to be considered the frictionless wheels, so that it can be easily moved on the surface, okay. And the tank, as I told you, this tank is filled of water, and which is a height of h from this exit center point of this exit of the water. So this part is actually the water supposed to exist from the tank, and when the water is coming out from this water, it will be considered the velocity v. So velocity v is the jet of water which is coming out from the tank, and though the orifice is fitted here, so to increase the velocity of the jet, we have fitted the orifice here. Now we can see if the tank is normally situated in the surface and there is no movement is there is no wheel is fitted in that. So obviously in that situation, suppose this is the tank and the tank is situated on the surface, okay. So here, if the water is coming out from here, there will be no problem. That means there is no movement on this tank, because the velocity of water which is coming out, or that we can say the force which is created by this jet of water, okay, that is not sufficient to move this tank from this position, So what are the forces generated by this jet of water which is not sufficient to move this tank in the backward direction? Though there is a reaction force is there, but the reaction force is not enough to move this tank. But at this condition, if you see here, the surface is there and two wheels are attached, both are frictionless wheels, and here the velocity of water which is coming out, this velocity of water is giving a reaction force on this, okay, a reaction force on the tank, and due to this reaction force on the tank, this tank also started moving with a velocity of u, okay. So these things we'll discuss in detail, and we'll identify some equations for this. So to derive this equation, let me consider some few terminologies or few parameters in this. So here, first one, I'll consider the h. So h is nothing but the constant head of water. This is the constant head of water, and from the center of orifice, we can say. So suppose this is the orifice is there, orifice is fitted. So constant head of water from orifice, this is enough, okay. And next is, if the orifice is there, means obviously we need to identify the area of orifice meter, the area of orifice. Similarly, next, the v, I've given the v terminology is there. So v is nothing but the velocity of, this is jet of water. Similarly, we need to consider another one terminology, that is u. So u, we can consider the velocity of tank, which is moving in the opposite direction. We'll discuss more in details in that, about that. Now another terminology we need to consider when the velocity of fluid is coming out and orifice meter is fitted here. So we need to consider one terminology, that is called CV. So CV is nothing but that is coefficient of velocity actually. This is coefficient of velocity. This is coefficient of velocity of orifice meter of orifice. So this when we discuss about the orifice meter, you can see that like why it is taken for what purpose. And here actually the coefficient of the velocity of orifice, how to identify, I'll tell you. So CV actually it need to be calculated by like the actual velocity by theoretical velocity. So what is the actual velocity of this fluid and what is the theoretical velocity of the fluid? So actual velocity actually we can calculate by this. Okay, if you write here VA equal to CV into root over of 2GH, and that is nothing but theoretical velocity. Okay, and theoretical velocity here we can write this is nothing but root over of 2GH. This is theoretical velocity and this is actual velocity. And this theoretical velocity is actually, it is given by Torricelli. This is actually Torricelli's law, theoretical velocity and actual velocity. From this we can calculate. Anyway, we won't discuss much in that. Just I'm giving a hint how to identify this, how to calculate the coefficient of viscosity. So though the orifice meter is fitted here, so we need to consider the coefficient of velocity of the orifice. Now the water which is coming out, we need to find out the mass of water. Next is the mass of water which is coming out from the tank through the orifice meter, we can say per second. So mass of water which is coming out from the orifice per second. Just writing the shortcut, mass of water coming out per second equal to, we know that this is we can write this is mass of water per second. So what we can write, already we have discussed many details about this terminology. Again I'm writing this one in on behalf of mass. We can write like rho equal to mass by volume, then I can say mass equal to rho into volume. So here I can write rho into volume by second. So this volume per second, here we can write this is discharge, and here we can write on behalf of discharge, again I can write this is rho V, rho AV, rho area into velocity. Okay, this is the terminology. Mass of water which is coming out from the tank through the orifice is nothing but rho A P. Rho equal to density, area equal to A equal to area, V equal to velocity. Now we need to find out what, once you find out the mass of water per second, then we can calculate the force acting on water. The force acting on the water, we need to find out, and which is nothing but which is equal to the rate of change of, momentum. The rate of change of momentum, because you can see when the fluid is started flowing, obviously its momentum changed. So what we can write, the force which is acted on the water, we can write F equal to the rate of change of momentum. That is nothing but this is mass of fluid per second, and we can write this is change of velocity, change of dV. This one also I'll tell you how I got this one. I can write this is F equal to mass into acceleration as per the Newton's second law of motion, and this one in the place of mass I can write mass, and acceleration I can write dV by dt. Acceleration equal to change in velocity by change in time. Again change in velocity I'll write here, I'll keep it as usual, and time I can just I'll put this mass per time. So a mass per second into this change in velocity. So change in velocity dV. So this one again, the mass per second, we can write this is like rho AV into this change in velocity. So change in velocity is nothing but here we need to consider actually what is the final velocity. Final velocity minus initial velocity. So what is the final velocity and what is the initial velocity? Here we need to find out. So the change in velocity actually that need to be taken final minus 1. Why? Because the force on water, we are finding the force acting on the water. Okay. Initially what we have calculated? Initially we have calculated the force exerted by the water. exerted by the water and on the water. That is the two different things. Force acting on the water, that means final velocity minus initial velocity. Force exerted by the water in the sense initial velocity minus final velocity. That is the difference. So that's why we need to consider in this way. Now here the initial velocity what and final velocity what? Final velocity, the velocity of water which is coming out here. Okay. And what about the initial velocity? So initial velocity means the velocity of fluid which is present in the tank. So in the tank you can see there is no movement of the fluid. So here velocity equal to 0. So what we can write here? You can write the force equal to, this one you can write rho AV into final velocity. Final velocity is nothing but V. And what about the initial velocity? Is 0 here. I hope you understand. Like what is the final velocity? That means the fluid which is coming out through this orifice to outside, that is the velocity of the jet. And what about the initial velocity? Initial velocity in the sense like the fluid from where it comes out. So the fluid which is present means it is present in the tank. So in the tank the velocity of water is 0. So we can write this is rho AV square. Okay. This one we can give an equation. Equation 1. So the concept of this, if you see, okay, the concept of this is actually already I told you. The force here, the force F, this is the force F, which is the force exerted by the water. The force exerted by the jet of water, where when the fluid is coming out from here, from the tank. So this jet of water actually which exerts a force on the tank also. On the, actually if you see this one, this force also equal to this force which is reverse force. That means as per the Newton's third law of motion, every action is having a equal and opposite reaction. If this is the action is there, this is the reaction part. Okay, so this force and this force both are equal. That's why the force which is acting here will be equal to the force which is exists from this. Okay, so due to this velocity, the fluid which is coming out, that gives a reaction force. So that you can see there is this movement of this tank started moving in the reverse direction, opposite direction. That's why here U, okay, here U already I've written here, velocity of tank. Okay, now we cannot consider the velocity of jet here because due to this velocity of this jet or this force, okay, the tank started moving. That was velocity of fluid is coming out, the tank also started moving in the reverse direction. So there is two different velocities are there, two different movement of objects are there. So in this case we need to consider the relative velocity. So we need to find out the relative velocity of the jet with respect to tank. Okay, we need to find out VR, relative velocity of jet with respect to tank. Okay, we need to find out. So relative velocity already told you, when two objects are moving, okay, with different velocities. Suppose this is VA and this is VB. So we can find out VR equal to VA minus VB. So VA minus VB in the sense relative velocity at VA equal to VA minus VB. Okay, we can find out like this. So here also VR, as I told you, VR equal to the relative velocity of jet with respect to tank. This one we need to find out. Okay, yeah. So one more condition also I told you, if this tank is on the surface, it won't move. So here the wheel which we have fitted on the tank, due to the frictionless concept, the tank started moving in the opposite direction. That is the concept here. Okay, now here we can find out the VR. So VR equal to, we can write the velocity, what we can write, the vectorial difference between the jet of fluid and the tank of velocity, tank velocity. That means we can say now absolute velocity V. Now here this V, what you have written, velocity of jet of water. Also I can say this is a, I can consider now absolute velocity. When you calculate the relative velocity, at that time we need to consider this is a absolute velocity. So that is V minus the velocity of tank, that is nothing but U. Now if you see, the U is moving in the reverse direction. But here what I told you, this one, this is v, suppose this is u, so we can write v minus u and we can find out the relative velocity. But here the u, that means the velocity of the tank which is moving in the reverse direction. Our jet moving is one direction velocity, this is reverse direction, so which is opposite, in the sense we can write this is v minus of u. Okay, so which is moving in the opposite direction, so we can write v plus u, v plus u. So when the tank is moving, we can say the velocity of jet with which the fluid which is coming out, we can consider v plus u. So we can write the mass of water which is coming out from the orifice. Again, we need to write, see here we have calculated already mass of water, but only for jet. Now when you compare with the relative velocity, then it will be different. So in that case, we can write the mass of water coming out from the orifice, okay, coming out from the orifice per second. We can write here, this is rho into A into velocity with which the water comes out, velocity with which the water comes out. That means we need to consider VR, not the V. So here we can write, this is rho A, here V plus U. Okay, initially it was only rho A V. You can see it, initially it was this one, this is rho A V, but here we got V plus U because relative velocity is considered here. Similarly, once we find out the mass of water, then we can calculate the force or the force exerted on the tank. The force exerted on the tank equal to, you can write, this is Fx in the direction of movement, you can see that is x direction. So we can write, this is the mass of water coming out from orifice per second. The mass of water coming out from the orifice per second into the change in velocity into, we can write, this is dV. Okay, so here what I can write here, the equation I can write, this is Fx equal to mass per second, already I have calculated, that is nothing but rho A, here V plus U, and this is change in velocity. Again, change in velocity means that is final velocity minus initial velocity. Now here we can write, this is V plus U, and this is initial velocity, here it is U is there. Okay, and now you can write, if you solve this one, you can see this is plus and this is minus. Okay, so remaining how much is there? So you can write, this is rho AV bracket V plus U. Okay, this is, you can give equation, another one equation, we can mark it equation number 2. I hope you understand this equation. This is change in velocity. So here also the change in velocity means what is the final velocity and what is the initial velocity. So final velocity in the sense the velocity of jet which is coming out. So velocity of jet is coming out, initially it was V. Now we have considered this is V plus U, relative velocity. So relative velocity minus the velocity of tank or initial one. Okay, now this is about the force exerted on the tank. Okay, once the force exerted on the tank is identified, the remaining part is work done and efficiency, because there is a movement of the tank is there. So we can find out the next step, we can write here the work done of a moving tank. So the next step is, we can find out the work done on the moving tank, the moving tank by the jet, moving tank by the jet per second also can be calculated. What is the formula for this? It is nothing but Fx into distance per time, force into distance for time, distance per second, because how much distance traveled. So that is nothing but distance for time second, we can write velocity. Okay, so velocity we can write here Fu. So Fx already calculated here, So rho A, this is V plus U into U. U is the work done on the moving tank. So how much the tank started moving. So that is how much distance traveled with respect to time, that is velocity. So this is our efficiency. This is our work done. Once we calculate the work done, again we can go for the efficiency calculation. So efficiency of the propulsion can be calculated. So this is efficiency of propulsion. We can calculate. What is the formula will be this for this one? That means work done per second. Work done per second. This one, work done per second with respect to efficiency equal to output by input actually. So output is nothing but work done per second, and input is actually, this is kinetic energy. What is the input is? Kinetic energy of the jet per second. Kinetic energy of the jet per second, that is initial conditions. So what is the work done already we got here? So work done is nothing but, already you can write, this is rho A B plus U into U. This is our final work done. And this kinetic energy of the jet issuing per second is nothing but, we can write half mv square. And this one we can write again half into the mass of water per second. The mass of water per second. Mass per second into the velocity. Into the velocity of issuing the jet. Okay, so issuing the jet in the sense relative velocity need to be considered, as simple as that. So here what I can write here, this is again I'll write here, this is rho A B plus U into U with respect to, we can write this is half mass per second. This is rho A B plus U, rho A B plus U. Yeah, here actually work done, one more V is there actually. Here we can write one more V is there. Yeah, here mass is there, rho A B plus U, and this is velocity of the jet half mv square. This is actually, we can write square, velocity of the jet square, and that is nothing but, we can write this is V plus U square. Okay, now if you see, this term and this term will be cancelled, very simple. So what we'll get here, and here one more V is there. Okay, so what I'll write here, this 2 denominator 2 I can take it to the numerator. So you can write this is rho small u capital V divided by, this is V plus U square. This one again we can give an equation number 4. This is our efficiency. This is our efficiency, and this is our work done. Okay, now actually we have another terminology is there, like what is the condition for maximum efficiency? Okay, or what is the expression to find out the maximum efficiency in that? So for a given velocity of V, the efficiency will be maximum when, we can write, we need to write derivative of this efficiency with respect to U equal to 0. So what we can do here, let's write, what is the equation is there, derivative of this terminology is there, 2uv divided by u plus, here we can write, sorry, v plus u square bracket close d with respect to u equal to 0. Just we need to derivative of this. Then let me write derivative of this u, and this is there. So we can write in the other term, we can write it like 2uv into, let the denominator part, let take it to the numerator. So v plus u to the power minus 2 equal to 0. Okay, now what I'll do here, again one more time I can write, this is like this derivative part, let take it to the right hand side 0 and make this terminology free, or we can do derivative of this, not right hand side, we will do this derivative of this. So derivative of 2uv, so you can write this is 2vu, okay, and into we'll do this one otherwise. This is whole square is there, so whole square we can just open it, and finally we can write this is 2vu into minus 2 into minus 2 here v plus u minus q plus this is v plus u to the power minus 2 into 2v into 2v equal to 0, okay, equal to 0. And now what I'll do here, or we can write this here, you can write minus 4vu divided by, okay, let's take this terminology here, this 2vu minus 2, that is minus 4vu, and this minus to the power minus q is there. So this one I'll take it to the denominator size. So that means we can write v plus u whole cube. Just I have taken this terminology down, denominator, and this one I have multiplied with this. Now again plus 2v is there, so here write 2v divided by this whole minus q is there. Let's take it to the denominator, v plus u square equal to 0, okay, equal to 0. Now again we can write this terminology in other way, like yeah, if I take this LCM of this, what will get v plus u q, okay, and I'll take it to the right hand side, I'll make it 0. Then if I solve this one, so LCM is like, you know, will we get v plus u q. So in the top it already same term is there, so you can write 4vu plus here v plus u square, so one more v plus u will be multiplied here, that means in the numerator, so that will be 2v, here again v plus will be multiplied equal to 0. Just take this term to the right hand side, make it 0, okay. Now what I'll do here, just divide 2v in the equation. So if you divide the 2v here, what will get? So this will be minus 2u plus v plus u equal to 0, and we can write this is minus u plus v minus u, just you solve it, minus 2u and u, so you'll get minus u plus v equal to 0, and finally we can get u equal to v. This is our equation. Now this equation you can put in the above equation. So this is the condition of maximum efficiency. This is the condition of maximum efficiency when u is equal to v. That means the velocity of the tank is equal to the velocity of the jet, okay. When it will be equal, then we can get the maximum efficiency and put this value in this above equation. So we can write the maximum efficiency equal to what is the equation is there, 2 into u into v. So you can write here 2 into u into u divided by u plus u square, u plus u square. So finally what will get here, numerator 2u square, denominator what is that, 4u square. So finally it is 1 by 2 and nothing but 0.5, or we can get maximum efficiency we can achieve here, which is 50%. This is our answer, okay. So this is the derivation about this jet propulsion of a tank with an orifice meter. I hope you understand this concept and theory part. If you are having some kind of query and doubt regarding this, you can give a comment in the comment box. Thank you all.